So for the next session, we're going to have Konrad, who's just joined us right here. Hey, Konrad, how's it going?
Hey, yeah, thanks for having me.
It's our pleasure. So Konrad is going to bring us JDK9, Reactive Streams, and Akka Streams in the real world. That's awesome. And we're also going to have a new JUG that's going to participate with us here, which is going to be the Bangalore JUG. Hey, Bangalore, how's it going?
I'm sorry, this is not Bangalore. This is Bangladesh JUG.
Oh,
we call it JUG BD.
Sorry, I think that that was kind of like a.
It's okay. We're from Bangladesh.
Yeah, I'm sorry. I guess it was some mistake here on the doc. And yeah, so this session is gonna it's brought to us by Lightbend. So Lightbend is actually the former TypeSafe and is a company that works mostly with Scala programming language. They're the creators of the Akka middleware, and they brought some other products like the Play framework and most recently Legume for microservices. So I know that Konrad's been working a lot with the Lightbend stack, right, Konrad? So I'm guessing you're going to talk a little bit about what you're doing over there, right?
Yeah, I can share a few words.
Awesome. And I know that you just recently moved to Japan, is that correct?
Yeah, I'm in Tokyo now. Which is,
oh, awesome. How is Japan treating you?
Very well, actually. Enjoying it.
Okay, that's great. So I'm going to give control back to you, Konrad, so you can start whenever you want. You'll have 45 minutes, and we'll try to keep like 5 minutes left for questions. So please feel free to start whenever you want.
Okay, so I'm sharing my screen.
Okay.
Should work. And let's jump right in. Okay, so in this session, we're going to talk about what's new in JDK9, which is basically the Reactive Streams manifesto. And I want to link it back to the actual implementation thereof, one of the many implementations thereof, which is Akka Streams, and what it actually means for the entire ecosystem. Because only all of these things put together actually have like a meaningful impact to the JDK ecosystem. So let's jump right in. So my name is Konrad Malawski. I work on the Akka team at Lightbend. I talk about Reactive Streams because I was involved there in building the TCK. So that's the technology compatibility kit, and yeah, also parts of the discussion. Other than that, yeah, before I moved to Tokyo, I was doing a lot of community stuff in Krakow. So you'll see here, that's the Krakow JUG basically. So it's the Polish JUG, but it's the Krakow JUG. The GeeCON conference, so it's coming up in May, or some reading clubs around functional programming or just computer science, that's STKRK. So for people joining who have no idea what Akka is about, quick brief intro. So it's a toolkit for building both concurrent applications, if you stay just in process in a single JVM, and distributed applications. And we kind of want that to become simple, because by itself it's not really, especially when you go distributed. So that's kind of the idea behind the toolkit. There's various parts to it. So there's actors, then the actual clustering if you go distributed. We have Akka Streams, which is the only part that will be somewhat present in this talk. But just wanted to clarify that, yeah, Akka is not only the streams part, it's a lot of other things. Then persistence for event sourcing, that's been stable for years now. So we've got a lot of experience in event source TQRS systems. And HTTP, that's our HTTP 1.1 and HTTP 2 server. I've maintained that for quite a while now. And maybe surprisingly to some people, all of our projects, including Play or whatnot, everything has a Java API. And it's not just a Java API that we slap on. It's, since the beginning of the company, also it's TypeSafe. We always had Java APIs for everything. So it's pretty much at the core of kind of the culture at TypeSafe and Lightbend now, which is to have feature parity and also feel nice also to Java developers. If you don't want to do the switch yet, because we find that many companies, organizations, they start with Java, but eventually they figure, okay, let's move on to Scala. So the subtitle about the book signing, that's not correct. I stole the slide from somewhere. But I wrote a mini book And if things that I talk about here you can interest you, then you can download this free mini book, which answers some of the questions about the most overloaded term in computer science right now, which is reactive. And I think part of the problem it's become so overloaded is that it has many meanings, but they all kind of play to one another. So that's specifically from the Reactive Manifesto's definition, which is the only definition that really was kind of put together thoughtfully, rather than calling a thing randomly just a reactive thingy. And you'll also see part of the confusion arriving from kind of the front-end people arriving to the word reactive thanks to toolkits like be it Angular or React, etc., where they basically mean that, yeah, there's a chain of events and UI elements react to things. So that's actually part of it, that things are message-driven, and that's really the solid foundations of this entire reactive thing. If you see anything that's reactive at the core of it, it really talks about messaging, if you see it or not, and we'll see that also in Reactive Streams and how that relates to JDK9's flow interface. And then the other things are kind of what you want to achieve, the reason to become reactive, right? You want to be resilient, you want to scale your services. And this brings me to this definition of reactive applications, which could be the streaming part, so FRP, things like that, so functional reactive programming. Certainly that helps inside the application. It doesn't quite solve the big picture. So if you're interested in what they mean by that, there's the free mini ebook from O'Reilly that you can just download. And the difference between the outside world and the inside world, as you see it, so one is the app, and inside the app you do stuff, and then there's like a broader system of many apps doing things with one another. And today's talk will be specifically about this touch point between the outside and the inside, basically. So before I jump into Reactive Streams and what it actually means, I want to kind of show an example that we faced in practice that led us to, then Victor went out and founded this Reactive Streams initiative, invited a bunch of other people, like the Spring people, the Red Hat people, and then we all figured that we should collaborate. But this was our kind of immediate need and what we discovered. And just in practice, building reactive applications kind of before it was cool. So what would happen is a customer or just a user, someone comes in, writes a new system using Akka. And Akka is pretty fast and can, thanks to its asynchronous processing and mindset, usually can handle incoming traffic or just send data through very easily. So it handles traffic like a boss. And then you handle it like a boss, and it's a new system, and you roll it out to production. Yeah, but no system exists in isolation. So what would happen is some other system wouldn't really be able to cope with the incoming rate of messages, and it would blow up. So nowadays, this has been maybe the trend of the year was that people would say, oh yeah, I'll just slap a Kafka in there to solve the problem. And what I found recently, so just this month, no, last month, one of the authors of Kafka, the Definitive Guidebook, tweeted this thing, that one issue that keeps coming up in Kafka Connect is that many downstream systems, so the green one over here, don't really scale as well as Kafka. So be careful to not DDoS yourself. This is exactly what we've been seeing for years in kind of just Akka-based systems. And the same applies to Kafka. Kafka scales well, Akka scales well, some other systems don't, and then we just start killing other systems. And that's, a good feeling on one hand. Okay, ooh, I wrote this fast system. But a really bad thing in reality, because, you're killing your internal company systems or some other external service. That's not a good thing to do. So here I'm kind of hinting at one of the solutions we arrived at for this specific problem, and we'll loop back to this Alpakka here. So another reaction that people would always have to overload problems is, okay, let's put circuit breakers in there. And To clarify, this is by no means I'm saying circuit breakers are bad. I'm just saying that it's not quite the best solution for this specific problem. So, okay, what happens is you have this overloaded system. Maybe it's just HTTP requests. And there's a good talk by Nitesh Kant on this entire subject. And then, yeah, it starts responding, but maybe it can't respond all the time. It starts blowing up. And what the circuit breaker would do is, or just a naive flow control mechanism, or from that other side, is that they'd start replying with just 503, or just with the circuit breaker tripping instead of being able to send the request through. And this is a diagram we have in our Akka circuit breakers since probably 2010 or so. And this concept is very simple. So if you failed once, you back off a bit, you keep throwing an exception or something, or just not passing through the messages to the downstream. And after this, a few seconds or minutes have passed, you try to reset the circuit breaker. So that's the attempt reset from open to half open. And if it works, then you start sending the messages again, right? So there's some exponential backoff maybe, circuit breaker opens again, and you start trashing the other system again. So I call circuit breakers the slamming the brakes pattern, because you basically have not throttled down, you have completely stopped sending stuff, and then you go full speed again. At least this is how in practice I see people use circuit breakers. Does it help? Absolutely. But by the time you slap the brakes, you've gotten to this state. Okay, so we've gotten to this state. Let's reset the circuit breaker. Perfect. Let's slam the brakes again, etc., etc. So this specific case, well, it kind of helped, but is it really the best we can do for just flow control? Because for failure control, so okay, we have a downstream failing. Okay, so the node is really in trouble, and we really want to stop hammering it. So that the failure is different than just flow controlling the rate at which we're sending requests. So circuit breakers, awesome for handling failure, not awesome for handling like a nice even flow control, so that you go as fast as you can, but not faster. And the other problem with circuit breakers is that usually people hard code the values for how long should a request take, etc., and then the circuit breaker triggers. But that is a lot of guesswork. And okay, if you have one circuit breaker, that's maybe manageable. You'll figure out the timeouts or something. But you don't have one, you have a lot of them. And there's a lot of guessing going on. Obviously, you could auto-tune them or something. I've never seen people do that in practice. Even today, we had a customer say, oh yeah, we'll be back soon. We're tweaking the circuit breakers. That's not something you want to do. It should just work. So this is how we arrive at reactive streams. So you have this fast upstream, and you have the slower downstream. And with reactive streams, we generalized this concept. So this is nothing new, really. The problem has been around just in queues, when you build an asynchronous queue with many producers, many consumers, and we insert or pull from the queue asynchronously. Basically, same problem. But we wanted to kind of standardize this protocol, that many implementations would do the same thing. So it's a building block for reactive systems, but it's not quite the reactive kind. It doesn't magically make your system reactive. Okay, so why do I talk about this? Was involved quite early on, did the TCK, still am doing the TCK. And why is this a topic right now that is really hot? Because it's part of the JDK9. Right now, if you get JDK9, it's the first point of the more concurrency updates, JEP. So you'll hear me talk about reactive streams, but right now I think we should be transitioning to using the term flow everywhere, because Java util concurrent flow is exactly a one-to-one mapping of reactive streams. So we have a TCK. It also works and defines the exact behavior of flow. Yeah, and just just a nice link that we're also supporting JDK9 right now, and we're supporting Flow in Akka since the day JDK9 was released, basically. So you don't really have to wait to use that interface. But would you really use that interface directly? And the answer is a bit surprising, because other than, let's say, like Raphael's talk a few minutes ago about the modules, this is something you'd interact with directly, right? I mean, if you want to write a modularized app, you will have to directly write a module info class, right? So it's a very direct thing. Whereas Reactive Streams is really something you'll be more aware of that it exists, but maybe you wouldn't see the types at all during development of a reactive app with them. And that's because they're more of a service provider interface, kind of like JDBC, but in practice you'd use something on top of it, etc., etc. So now to disambiguate what stream means. We kind of talked about the other ambiguous word, which is reactive. Now let's talk about the second most ambiguous word right now, which is stream. So stream, in the wording, at least how we see it in Reactive Streams, is a element by element, possibly infinite, well, not a recursive definition, but stream of events, source of events. And what's the goal of Reactive Streams again? So we talked about the back pressure mechanism. I haven't mentioned the word yet, but we kind of have, about this flow control, etc. And the second part of its goal was interrupt. Because when we built Reactive Streams on the outside of the JDK, we kind of intended for it to become a standard that maybe would be included in the JDK if it's successful. And this has happened, actually. So while Reactive Streams was being developed, we had people from the RX Java ecosystem, obviously. So Ben Christensen, very important person in the project. Reactor, like the Reactor people back then was John Brisbane, and now it's Stefana. Vertex people, and who else was there? Well, obviously Oracle, kind of, and Doug Lee also looking at it if it starts to make sense or not. And all of these implementations implemented the same Reactive Streams interrupt protocol, which we'll explain in a second now. So just fast forward, okay, Reactive Extensions was good inspiration for RxJava. And RxJava, I'm kind of jumping between things. Okay, let's do that. So, bottommost point about Ben Christensen starting RxJava. So RxJava is very much inspired by the Reactive Extensions, right? So it's 2009, basically. And what it didn't have when it started out was the back pressure. It was mostly concerned about just the model of the observable, that, okay, you subscribe to stuff, and you'll be getting some events. On the other hand, Play already back then had some thoughts and needs around supporting back pressure. They solved it using iteratives, and we were kind of doing the low-level, kind of exposing the OS semantics to you, which was just the negative acknowledgement semantics. So not very pleasant for users. And then when we looked at this, it's okay, RxJava, nice API, understandable. Our back pressure, a bit complicated, high-performance stuff. Play had this pull-based back pressure, but the API was very, very difficult. So just by looking at the signature, it doesn't really speak to you how it's meant to be used. So Play dropped that. Reactive Streams kind of working group gets founded. Roland, Eric Meyer, Ben Christensen get involved. And we finally arrive, and then Stefana and other people arrive at the working group. And we finally arrive at JDK at a successful release of Reactive Streams. So we had all these many libraries implementing the same thing. We've proven that it's useful. We've proven that the interrupt works. And then it was considered for inclusion in the JDK and successfully included in the JAP266. So now, basically, this is what you have in JDK9. I used to have this slide up with this soon marker. Now I can actually say, now it's part of the JDK. So these interfaces are all there is to it. Well, there is a very simple implementation in the JDK, but currently JDK9 doesn't really have any implementations thereof, except this one submission publisher, but it's a very limited example. So why would we actually want these interfaces in the JDK? And well, they seem deceivingly simple, but actually there's a huge set of rules and a specification around how to use them. Yeah, I'm trying to find one which would maybe signal how tricky those are to implement. For example, a subscriber on subscribe must be called at most once for a given subscriber. So it cannot be called twice. That would be illegal. So there's a lot of rules like that you don't really see just by looking at the types here. So don't be kind of tricked into, oh, so simple. Rather, you would want to use an implementation of Reactive Streams, of Flow, to use those. So, but let's talk about what it actually does, because I think understanding what it does not conflict with, you don't have to implement it yourself. And understanding what it does will then help you understand how the system behaves in practice in production. So kind of like we talked about this two servers case where one was trashing the other with too many requests, it's the same situation here. So the right one, the subscriber, is processing the messages at 1 operation per second, and the upstream, the left one, is able to emit messages at 100 ops per second. Could be any number you pick there, as long as the upstream is faster, then we have the problematic case, right? So basically, the Reactive Streams protocol talks about, okay, let's assume I have some buffer space, and you always have some buffer space in practice, and you knowingly how much space you're willing to buffer, send a request to your upstream, which says basically, I request 3 elements, and then the upstream is allowed to send you up to 3 elements. And whenever they send an element, kind of the permit is used up. So if after sending those 3 elements, the upstream would have to wait, and it doesn't have to wait blockingly. It can just not generate elements or not pull elements from its upstream. So it's transitive in that sense. And by that, we allow for safety. And by allowing for this element to be free and also cumulative, we allow for this to be batched and really efficient if both of them are really fast. So, like I said, we support the JDK types already, so I will try to talk about Flow from now on instead of Reactive Streams, because it's exactly the same thing. And the interop thing, as an example, this is how libraries can interop using that. So I talked about this protocol, and now you can see whenever you have a be it a publisher or a source, what other name do people have it for it, like Flux or something else, all these can interoperate safely because they all know this protocol. And here you see all of the various implementations. There's Reactor. For Reactor, I think I have the old name. But for Akka Streams, it has been and always will remain source. In RxJava, it will be flowable now, etc., etc. So let's look at Akka Streams for a bit. So this is how Akka Streams look. And you'll notice we have a bit more type information. When we were working on Reactive Streams and Akka Streams for 2-3 years or so, we noticed that a popular use case was to, okay, you have a source of integers, but you also sometimes need to kind of talk with the outside words from the stream. So here it's not interesting, okay, it's some source of integer, whatever. A flow, okay, so that's a transformation of integer to string. So it's a map operation, very easy. But the sync gets interesting, because what you want is, okay, if that sync is completed, if that stream is completed, I want to have this signal to the outside world that, yeah, it's complete. Actually, let me fix that example. How many times have I presented this and never noticed? Let's do run with. Actually, I know what I have. So let's also do just run with sync. And this would give you the completion stage. Basically, what this means is we have a type-safe and built-in way to talk from within the stream with the outside of the stream. And each of the processing stages can do that. So here another example how all of this would look in one line: source single, map to string, and then you run with, and this head basically takes the first element and returns it to you in a completion stage here. So you can just do normal, hand it out as a future, etc. Very useful bridge between the two words. Typing-wise, maybe you've heard the popular complaint that Akka is not typed. That is not quite correct. Akka is fully typed in the streams. We also have a Akka typed project, which is fully typed actors. So we're actually addressing this Akka being untyped thing very aggressively. And when you think about these things, because we have various words for the stages. We have source, flow, sync, and the power user mode, which can do anything. But we think it's very important to be specific about, okay, is this a transformation? Is this a source of data? Versus some of the other libraries which have one word for kind of all kinds of stuff. Like flowable could be anything, right? Interesting kind of side note. And another thing that kind of is different in Akka Streams than in other implementations is this materialization stage. So when you look at this thing, up until when you see the word run, it doesn't do anything. So in some people would like to call this a cold stream, but it's not really cold. It's just started at the moment you tell it to run, right? The source can still be hot. So it's not quite that distinction. And we have a blueprint, and what we do when you call run, we can fuse it, we can interpret it, we can optimize it, and then it actually runs. So we have a full graph description of all of your stages and how they connect and what they do, and then we can kind of emit an optimal version of it. This also allows us to have very nice introspection capabilities without having to hack them into the thing, right? So just by dumping this blueprint into a dot format, we have this nice graph, but yeah, that's like nice for development, but we're actually working on something that would do that, but in production running graphs. Okay, so now we have these sources and sinks and flows and whatnot, and we also get reusability through encapsulation. I mean, you can build a bigger source that's composed of other sources and flows, and we'll get to that because we think this is the actual power of reactive streams and flow. So you can build one thing, it's a flow, it transforms acknowledgements to emitting new data, for example. Or you can have a thing that just consumes the X and a separate thing that emits the data. And it all fits together in a nice type-safe way. And a collection of such pluggable sources and sinks and flows is something that we started almost a year ago, which is the kind of project Alpakka. It's a code name for basically a collection of many connectors to stuff. Or the buzzword kind of pitch for it would be reactive enterprise integration. Why enterprise integration? Because very often you have these projects that are focused around just shoving data from one place to the other with some slight transformation, ETL style. And we have connectors to basically all of our ecosystem, of course, to all of kind of Amazon ecosystem, some Google APIs, some HBase APIs, Hadoop APIs, etc., etc. And that's only a mini subset of the list. And if you want to, you can always plug through the stream into the camera connectors and use the existing camera things. So that's why we called it Alpakka, kind of like a camel, but with more Akka in it. Verify, why not just use camera? Because Camel's threading model is inherently a bit dated. Back then it wasn't a big problem, but now you have these big streaming pipelines, and you really don't want to overload your downstreams, etc. So we kind of took the idea of Camel with these many connectors, but lifted it up to the world of reactive streams. And So while we do work on it a bit, it's more of a community where people contribute these connectors, at least right now it is. And a few months ago, we had a few connectors, AMQP, some Cassandra stuff. But right now, it doesn't really fit on a slide anymore. And yeah, it's still growing. We have a lot of connectors to more popular things and also less popular things. I know some people were interested in IronMQ. Personally, I've never used that, but because the community is driving kind of what we will build there, now it's there. And if you see a need for something, it's very easy to contribute connectors. Again, the power of composable elements. So to kind of showcase what it really means in practice, in the real world, what we envision this to mean in practice is, okay, you skim some dependencies. Yeah, I want to do something with Kafka. I want to pull stuff out of Kafka. Very popular thing to do nowadays. Then you basically have your Kafka source. You pick which of the kind of semantics you want. Is it at most once? Is it committable? Should it automatically commit when you pulled out of it, etc. Then you basically just pick that source. So the measurement source. You see what I did there. So here you have the measurement source of string, consumer plain source. So that's the Alpakka API to Kafka. And this is Akka HTTP, where you can just in a root say, okay, complete with this stream, and you're done. This is the entire, all of these, I don't know, less than 10 lines, is a completely streaming back pressured asynchronous pipeline that emits one of your topics. Completely. That's the entire app, plus imports. Okay, so, and then you profit. But what if actually I want to do a source out of some FTP server and watch the FTP server for a new file to appear, and then if it appears, stream the contents of that file? Well, you just change the source. You get the types to align, because this is FTP-ls, that gives me the file descriptors. So then I just want the FTP from path, and this already gives me a source of byte strings. And this I already could stream from my HTTP server. And again, profit. So this idea of these generic connectors that just work once the types align are very, very powerful. Basically, any Alpakka connector in that spot, and it just works. Could be also in any spots. Could be the downstream, could be an Alpakka thing. The downstream could be a RxJava thing if you want, because all of them implement the same interfaces underneath. They just can connect, and it's still safe and high performance, etc. So really, I think this is the kind of invisible killer feature of the flow interfaces. Another example to kind of think about where it makes sense is Akka HTTP. And when you think about it, TCP is a streaming protocol, right? What do we mean by streaming protocol? Well, it's this stream of bytes, and you're at some offset of this stream of bytes, other than UDP, which is just message by message, right? And we actually model Akka HTTP, so our HTTP server, in terms of reactive streams, in terms of the flow interfaces. And this has been stable for 1 or 2 years now. Maybe 2 years, actually. And we've seen this really pay off in practice. It's very interesting what you can model with that, especially when, so when you see flow here, that's the Akka flow. Kind of the naming was, evolving over time. We stuck with source, flow, and sync, and now flow kind of means the JDK thing. Anyway, so what's interesting in the flow here is, it takes HTTP requests, it emits HTTP responses, but it also is able to emit multiple responses for a single request. Why is that interesting? That's interesting because that is exactly what HTTP2 is. That's the server-side push. So in the types, in the model, we've basically modeled what HTTP2 will allow applications to do in the foreseeable future. Not only that, we also model the actual HTTP entity as a source of byte strings. So byte string is like a byte array, but we have some convenience around it. And WebSockets are, again, kind of like a web server. They take messages and they respond with messages. A message by itself can also be streaming inside. So it's really buffers all the way down. And I want to explain one of the use cases here, specifically the entity, although all of this kind of feeds one into another. So if buffers all the way down, I mean that you have a source of tweets or something like that, or source of data, or source of IoT measurements, or something like that. And use Akka Streams or Flow to connect them together. And at some point, you hit the TCP infrastructure. So in our example, we have a TCP implementation that exposes reactive stream semantics, and it also has some buffer inside. But by the end of the day, that's the OS buffer, right? It's the send buffer. And the send buffer is managed by the operating system, and it will also stop pulling, or rather, stop allowing you to push data if the TCP back pressure kicks in. The TCP back pressure that has been always built in, it's a window sizing mechanism, and we translate one mechanism to signal back pressure, flow control, into the other. So basically, if someone on the other side of the wire is on a mobile phone, they go into a tunnel, they stop being able to receive the tweets because, well, they're in a tunnel, then the TCP connection will notice that and stop pushing data. That's how it works. Then we will notice that, and we will stop even generating and marshalling the tweets. We can notice that suddenly this flow control has become a first-class citizen inside of your application. So pretty powerful abstraction to be able to lift that up to that level. In practice, some APIs already use that information. So the Twitter API, well, they don't use Akka Streams. Neither do they use Reactive Streams for that, but they basically reinvented the same semantics, because when they start buffering on the server side, they will sometimes start sending to you, to the user, to the wire, that, hey, you're falling behind and you're 300 tweets behind. Once you hit 500 tweets if in our internal buffer here, then we will disconnect you because you're being too slow. So you can start building actual logic around this back pressure concept. And I think this will be more and more interesting as we approach more IoT, etc. applications. How does that full example look like? So this full example that I showed here, again, omitted the imports, but still fits in one slide. And this is in Java. So an entire HTTP application with full streaming of tweets and back pressure and everything is basically that. And the streaming part is basically that you have a source that implements a Reactive Streams, so a Java util concurrent flow publisher, where it exposes the semantics thereof, to be precise. And then you just complete a request with it, and the streaming just works. So really powerful thing here. How does the same thing look in Scala? Obviously, just wanted to show kind of the feature parity. It's a bit less verbose, but the feel is exactly the same. You have a source, you complete with it, you're done. We can do a bit nicer kind of DSL style here in Scala, but really it's very much the same what you saw in the Java API. And a specific note about the Java API. It's not like some people sometimes think that it's an afterthought for us. We really intensely spend a lot of time on making the Java API look and feel nice. This API specifically, I think I spent 2 months perfecting, so that really uses all of the Lambda niceties and tries to do all of its best it can possibly do for Java to feel nice. Okay. So what's the adoption like? Because the entire promise of Reactive Streams, of Java util concurrent flow, is in the adoption. By itself, if only one library implements it, it wouldn't really make sense. So let's see who's adopting that, other than these libraries that I already mentioned, right? We need some real user adoption. So, well, real library adoption from big players, if you will. So the Amazon Web Services SDK announced that all of their streaming stuff in the upcoming version of the SDK will be implemented using Reactive Streams. So they'll also migrate to the JDK Flow interfaces later. There will have to be a transitional period, right? Because to be able to use JavaUtil concurrent flow, you have to be on JDK9. But we don't want you to require people to use JDK9 if they want to benefit from this ecosystem. So there is this period of time right now where libraries expose both interfaces, the JavaUtil concurrent flow interfaces and the Reactive Streams interfaces. And this is going to be for that, like, until libraries will be able to require people to use JDK9. So it could be a long time, but maintenance-wise, it's not a big burden for developers. So that's a good thing. Other things, so JDBC next, possibly JDK10 or 18.3, whichever versioning schemes will win. I call it JDK10 still because in the source tree, it's still called JDK10. So that's still under discussion, where exactly it will fit. Currently it is being used, but there's an active and ongoing discussion to make sure it really fits and really fits the exact semantics as well. So we'll see how exactly it will be used over there. If you're curious about that, you can subscribe to the mailing list. Feel free to chime in. I mean the JDBC next mailing list, to be specific. And here you can see the prototype was using it here on the result row. We'll see if that will be how it's going to be used or not. I think it may evolve quite a bit still. And another one that is actively, very confidently investing in flow interop is the HTTP client API, which you may remember has sadly slipped from JDK9. But I think this is actually a good opportunity for it to pull in JavaUtil concurrent flow, base some of its stuff around it, and have these few extra months to polish the APIs. So this is really exciting. We are personally in touch. We at Lightbend at the Akka team in touch with the team over there to kind of advise a bit of all of the things we've learned with Akka HTTP over the years. Because Akka HTTP also has a client, it also is Reactive Streams based. So obviously we found some of the tricky areas and want to help out the JDK team to either avoid or make these pitfalls harder for users to kind of bump into accidentally. So really exciting. As you can see, a body processor in the JDK proposal here. Again, this is not final API. It's an incubating feature. Could be released, could be not released. We'll see. But the proposal there was for a HTTP response to be able to give you a subscriber at byte buffers. So if you, not give you, take one from you. So if you look at that, that is exactly what we have over here in the, how we give you a sort of byte strings. So the JDK is kind of inverting that relationship, and it asks you to give them a sync, so a subscription. Both styles are fine, both work all right. They have just different trade-offs, which I can go into in Q&A if you want. Thank you. So the mapping is basically float subscriber means Akka Streams sync means body processor in the HTTP client. So last slide basically about what the rest of the Akka ecosystem means to the streaming stuff, and then we have some time for questions. Because people sometimes get confused when I do a talk only about streams, and they will ask questions like, does that mean that actors are not useful or something like that? And just wanted to proactively counter that because that question comes up each and every time. So specifically, if you model it as a complexity on the x-axis, on the y-axis, and modeling power on the x-axis, then okay, you have futures, not that complex. but very simple. You can't model too much in them because they only have one value that will possibly be there in the future. Then you have streams. Okay, more modeling power, more complexity. It starts to have more of a life cycle. You need to dance around things like completion, terminations of them, etc. But they can model more stuff. They can model infinite streams of data, etc. Then actors, they can model a lot of stuff. Basically, anything that you want to model as concurrent computation or location transparent computation, you can do that in actors. I would argue that typed actors bring the complexity down a bit. So that's, again, if you've seen Akka actors, they are very inspired by the Erlang model and have not been typed just historically. So typed actors bring back some of the sanity and some of the typed checkedness to actors. So check them out if you're interested. And then you have threads and logs and undefined concurrency models, which you just shouldn't ever use directly. So the stuff that Heinz was presenting today with, oh yeah, and you can copy-paste the type and do some crazy stuff, that is totally awesome. I love it. But perhaps this is not what you should be doing most of your day on a normal day job when you just try to get shit done. It's totally something you can do if you want to squeeze the last ounces of performance out of a thing. But you know, it's a trade-off of where you want to spend your time. So actors complement streams. It's not one or the other. And if you want to read up about that, excellent blog post by Colin Breck over here. Just read that. Don't take my word for it. Yep, we have some commercial stuff, but I'm not going to talk about that. So is it ready to adopt in production? Yes, absolutely. You don't have to wait for JDK9. You can start using Reactive Streams, and the switch basically is just changing the type signature. It's trivial, and when you use Akka Streams, the switch will be for you basically unnoticeable because you don't touch the flow interfaces at all. Here's some things you can just read more about Akka and find some guides, find some blog posts, and the documentation, of course. So that's just Akka.io doc. And that's all I had. The free ebook I talked about is available over here, just bit.ly reactive. So you can get that from O'Reilly. Some of the demo code that I did show a bit. We didn't do a demo, but just code and slides. You can check that out over here. And that's all I had. And I'm happy to take questions.
Thank you for the awesome presentation, Konrad.
Thanks.
I'm going to hand the word over to the Bangladesh JUG. Do you guys have any questions there?
Do you face any questions about the presentation content?
What does they mean by blocking non-reactive?
Sorry?
Blocking non-reactive.
Can you come over here? Just we have one question.
Can you relay it for us, please? Or have the person coming here and...
Yeah, he's coming over here and he's going to talk.
What does you mean by blocking non-Java, non-blocking non-React Java?
What do you mean by non-blocking?
Yeah, non-blocking reactive.
Non-blocking reactive Java.
Yeah, I want to...
he just wants to get a little more explanation about that thing.
Sure. So by non-blocking, we mean, for example, you have a... Let's take a simple thing. Let's say you have a file, and when you access a file, when you write to a file, you can do it in two ways. You can do it blockingly, which means, okay, here's some data, please write it to the file, and then you block the thread that is doing that write. And the problem with those APIs is, if you want to go really high scalability, is the number of threads is really limited. You can spin up more of them, but it's not helping performance at some point anymore. And when you blocked one, then you kind of wasted it. And you can do the same write in a way that says, okay, write this stuff to the file, and let me know when you're done. And Linux and stuff have APIs which can do that. We can access those from Java as well, and we can do the same kind of stuff for selectors, so for networking. And this allows you to keep less threads, and they can continue doing stuff while the I/O operation is doing its own thing in the background. And it will let you know, hey, I'm done, you can send me the next batch of data. So that's the non-blocking style. It's usually a bit more complex to code against, but we encapsulate it in Akka Streams, for example. You just have a sync file, and it does the async stuff for you.
Okay, thank you.
Thanks.
Do you have any more questions?
Yeah, any more questions from the Bangladesh judge?
So basically, we were trying to consume the content. I'm sure we'll have more questions in future, but we're basically overwhelmed with a lot of contents. Hopefully, we'll get there. Thank you for the presentation. Obviously.
Oh, thank you. And I'm guessing that I'm pretty sure that Konrad will be happy to answer any of your questions on Twitter or
Yeah,
offline.
Sure.
Tweet me.
Yeah, and I think that I'm not sure if you have any questions on Slack. At least it doesn't seem so.
Okay.
So I'm thinking that I'm gonna let you go, Konrad. So thank you so much again for joining us and do these awesome presentations.
Thank you very much.
Yeah, so see each other again sometime.
Yeah, see ya. Good luck with the rest of the day.
Yeah, thank you so much. And now we're just gonna make a small break. Bangladesh Jug is gonna keep with us for the next session, right?
Yep.
Yeah, and basically we're gonna start the next session in 7 minutes or so.
Okay.
So please keep with us and enjoy the short break to grab something to eat, go to the toilet or something else. Okay. See you in a while.
Thank you.
Thank you.